Namaste. Let us start the next lecture of this final week on the course of physics of nanomaterials. In this week, we are talking about the characterization techniques for nanomaterials. In the previous week also, we had looked at some of the important and commonly used techniques, and now we are slightly extending our discussion towards the use of more expensive or more involved techniques which are used to characterize nanomaterials. These are high-end characterization tools, but now commonly available in most of the institutes across India. You can just make samples and contact some of the institutes in and around you, and I am pretty sure they will be happy to help you to characterize the nanomaterials you are going to synthesize while keeping some application in mind. As we move towards Atmanirbhar Bharat, it is important that along with energy security, we also ensure material security, because it is clear that having independence in materials will only leave you in a position where you will have the independence and the flexibility to choose the devices which should be fabricated and which are relevant to your country. Otherwise, you will always be tuning your requirements as per the devices which are being fabricated somewhere else. But that is not always true. You must have devices, equipments which cater to the society directly, and we are doing justice to the taxpayers' money. So, let us now understand few more techniques which are there and are used to determine the surface structure. We will talk about low energy electron diffraction technique, the LEED, the reflection high energy electron diffraction, the RED, and we will compare the LEED with RED techniques, and then we will go to two very interesting techniques which were till some times back were not being used by people in nanomaterials. They were mostly being used by people who were doing characterization of bulk materials. But now these techniques are routinely being used to understand the properties of nanomaterials and correlate with the experimental observations. These are time of flight mass spectrometer or time of flight SIMS, secondary ion mass spectrometry. So, very interesting techniques which are now being used for understanding the surface structure of nanomaterials. When we talk about surface structure, what are we looking at? We are trying to understand the morphology or the surface structure, what is there on the top surface, because we have atomic arrangements, that is understood. And if you look into the 2D structures, then this is what you are looking at. So, this is what you actually construct. But when you start using such kind of samples, which surface actually becomes most important? This is the surface which is accessible from the top, and maybe up to certain level you have accessibility or diffusion or penetration of the incoming ions or electrons. That decides the usefulness of this material. Now, if you look into various types of surfaces, you can have surfaces, for example, which are very smooth. So, when I zoom this surface and take a 2D mapping, then I may find that you have particles which are very nicely arranged, or you have an array and the surface is very smooth. You have well defined potential functions associated with these particles. So, you have a ordered surface, but this is not always the case. What can you encounter? You can encounter cases where now if I make a surface, then I may get arrangement of atoms, but you also see some agglomeration on these surfaces. So, when I take the 2D mapping, I may actually start seeing something like this, and when I plot the corresponding potential, then I may see variations which are different, and because of this agglomeration, the size of the particles which are getting deposited would be different, and that drives the roughness. Now, you have the surface roughness. So, you can go from a very smooth surface to a rough surface. Each have their own advantages and limitations. So, you should have the capacity to actually start seeing these kind of features, because that will decide their usefulness for applications in various devices which are routinely being discussed in the field of nanotechnology. Some of the common techniques which are used are lead, read and time of flight mass spectrometer based investigations. So, let us start with lead. It is a powerful technique which is used to understand the atomic arrangement on the surface of mostly ordered materials. So, crystalline or polycrystalline materials. It is very similar to X-ray diffraction based studies, but works with electrons rather than photons. So, it is more like matter-matter interaction and not wave matter interaction. It uses low energy electrons which are having accelerations, or they are having energies in the range of 20 to 200 eVs. So, these electrons can penetrate only few atomic layers and they provide information of the surface. So, you can have various types of lead and they can be used to give you the qualitative as well as quantitative data about the sample. If you want to have qualitative use, then you will find that the diffraction spot patterns will reveal the surface symmetry. From symmetry, you can then go on and talk about the unit cell, the type of unit cell, the dimensions, and if you have those parameters, you can also talk about the expected growth mechanisms. And you can also talk about the absorbate alignment. If you are talking about quantitative use of these measurements, so you, for example, you have the intensity versus electron energy curves. Then you can compare these curves with the theoretical models and precisely get atomic positions, bond lengths and absorption sites. How is this quantitative value helping you? For example, you prepare samples at, let us say, 5 different temperatures starting from 50 degrees C, and you go on preparing the samples at an interval of 25 degrees. Now, as we know, when you increase the temperature, you have given more energy and the probability of densification increases and you may get larger size particles. When you have larger size particles, then their lattice parameters would be different. And if you are going to higher temperatures, you are giving enough energy for densifications, so you may have more compact unit cells and you may get different bond lengths. For example, let us take a unit cell. Why these techniques are important? It will become clear from some of these illustrations. We have been using similar figures earlier also. So, now you have, let us say, atoms at the cube edge and an atom at the body center. So, body centered cubic. You have bond lengths, various bond lengths. It is cubic, it is body centered, so all the bond lengths are similar. But now you transform this and you go to a state which is giving you more like a tetragonal structure. Now, the bond lengths would be different because when there is a tetragonal transformation, the atom at the body center either has a translation upwards or downwards. So, the distance of this atom to the plane of atoms below and the one above would not be equal. And what will happen? That will show you the appearance of a phase transition. Now, once you have a new phase transition occurring, you have a new symmetry appearing, and that changes the Brillouin zone, and as the Brillouin zone changes, you have different nature of energy diagram, and once I have different energy diagram or energy band diagram, my electrical, optical, even magnetic and mechanical properties change. So, just by understanding the values of bond lengths and making a detailed analysis of the quantitative values, you can understand lot of properties which are appearing in a material, and that is the power of such techniques. You just have to understand the features and go on putting what you know one after the other, and everything will give you a logical flow in the analysis of data. So, what are we going to do? You have an incident electron which interacts elastically with the surface atoms and leads to diffraction, because there is a periodic arrangement of the surface atoms. Now, you have a diffraction spot. This will provide information about the surface symmetry, unit cell dimensions, the surface reconstruction and absorbate ordering. Use the de Broglie wavelength in lead and you will get the corresponding wavelength of the electrons, which is determined by their energy as lambda is equal to 1.226 upon under root E in nanometers, and E is in electron volts. For example, if you have 25 eV, lambda is approximately 0.244 nanometer, which is close to the atomic spacing in solids, and so you can use this for carrying out the diffraction analysis. So, you have low energy electrons which are ideal for determining the crystal structure periodicities. This is a typical arrangement. You have the crystal, the electron gun, the electrons fall on the crystal, and then you have a fluorescence screen and you collect the scattered or diffracted electrons. From here you can then back calculate the arrangements on the surface. The lead diffraction pattern corresponds to what? It corresponds to the reciprocal lattice of the surface unit, and the spot position will give you the lattice constant and symmetry, whereas the intensities will depend on the z coordinate and absorbates. You can have multiple scattering effects which are often present in lead data, and therefore you have to correlate your findings with the theoretical modeling, which is given by the dynamical lead. So, this is what you can easily determine from the lead measurement. If you take this model of the scattered electrons by atoms in the topmost layer of a solid, and this is the way the typical intensity profile looks like. The sin theta is proportional to 1 by under root V, since lambda is proportional to 1 by under root V. And sin theta is inversely proportional to the lattice parameter A. So, you can find out the arrangement of atoms. You can use this data. For example, you have a FCC face centered cubic surface, and then from there you can calculate the lattice parameters, and you have the lattice vectors, and you can calculate the arrangement of the whole atoms or lattice which is forming particles, and these particles are arranged on the sample surface. So, this is what the whole data looks like for a 2 cross 2 structure. You can have a reciprocal lattice or you can take a real space data. Now, if you take the real space data or you take the lead pattern, then you have the corresponding data looking as the one which is drawn on the right hand side. So, in these patterns you can see circles are 1 cross 1 substrate spots, while the dots are superlattice spots. You can have the mechanisms which can drive the adsorption, and this gives you the different capacities to undertake qualitative use of lead, or you can have the quantitative lead experiments, and this is what we discussed in the slides before. The advantages are quite a few. For example, it is extremely surface sensitive, provides direct crystallographic information. It is non-destructive because you are taking low energy electrons, and it can investigate both clean as well as absorbate covered surfaces. But there are certain limitations. Mostly you will be able to investigate well ordered single crystal surfaces. The requirement for ultra high vacuum is there. Sometimes if you are not well versed with the technique, the data analysis is not a trivial exercise. If you have absorbates which are not very stable mechanically, then you may have these electron beams damaging the absorbates, and from there you can directly understand the applications of lead in determining surface structures to determining the absorbate positions which have direct impact in the area of catalysis. You can go to next, that is read, and here you use, instead of low energy electrons, you use high energy electrons, and you have the electrons which are incident at the grazing incidence, because the electrons will then interact with only the top few atomic layers, making this technique highly surface sensitive. And then again you can carry out the various studies just like in the previous case. So, if you look into a read pattern, this is the arrangement of the whole apparatus and the physics behind it, and this is the real experimental data. So, by analyzing the diffraction data, you can find out the lattice parameters. So, the diffraction patterns which you see appears as streaks instead of sharp spots like lead. These streaky patterns indicate flat surfaces, spotty or ring like features suggest rough or polycrystalline surfaces. And the intensity oscillation in reed signals towards the atomic layer by layer deposition, which is very common in the molecular beam epitaxy method of obtaining epitaxial growth of nanostructures. So, it is a real time in situ monitoring, but it works under high vacuum and it can give information about structural and kinetic data. So, using these you can compare these two techniques, and I will leave you to read this slide, and if you have understood the previous slides, before you start comparing these two techniques, first what you should do, write the features of lead which you have understood and then write the features of reed which you have understood, and then compare those two notes and prepare a table. Once you have done that, compare your writings with what is written on this slide, because we have discussed each and every point previously. We are just putting those informations together in this one slide. So, try to complete this exercise before you read through this slide. The next very interesting and commonly used technique is the time of flight mass spectrometry, where you have the technique which is used to identify the molecular species on the surface or in the prepared nano systems. So, this is what you can see is the feature which you obtain for fullerenes. What happens in this? What do you do? For example, let us say time of flight secondary ion mass spectrometer. So, you have an ion generator and you have a sputtering beam and you have a detector. There is a sample. So, there is a primary ion beam and then there is a sputter ion beam. Focus it on a small size sample and you have the ion generator giving you the beam, then it releases the ions from the surface which are collected by the detector. Then you use the sputter beam and ablate few layers from the top and then carry out the same experiments again. So, you can do depth profiling, first layer, then ablate it, remove it using the sputter ion beam, second layer, third layer, fourth layer and so on, so forth. And the thickness of the layer which will get ablated would depend on the energy of the sputter ion beam. And you can then easily get the 3D maps of the ion species which are available on the surface, and also you can get information about the depth of the sample. So, it is a very simple technique, just involves certain instrumentation which can be quite extensive, but the overall principle is as simple as the ones we have discussed. You can get, for example, for sodium manganese phosphates, you can easily have a SIMS data and you can find out the mapping of various samples. So, you can clearly see sodium is distributed, manganese is distributed, phosphate is distributed and oxygen is distributed, and that gives you the combined sodium manganese phosphate studies. And you can see how the ions are distributed on the surface of these samples. I hope now you have clearly understood the next few techniques which are used to understand the surface structure of nanomaterials. So, using X-rays, SEM, TEM and techniques like lead, read or SIMS or time of flight mass spectrometry technique, you can get lot of information about the samples which you prepare. So, now you have knowledge about nanomaterials, how to synthesize those nanomaterials, how to characterize those nanomaterials, and we have also discussed the applications of those nanomaterials, and that is where the technology comes into picture. These are some of the other references which would be very useful to read to understand more about the topics covered today. And thank you very much for attending the second lecture of week 12. Thank you very much.